Okay, let's have a look at problem 2316. Count unreachable pairs of nodes in an undirected graph. So for this problem, we're going to share a union find and a count solution. So and also we are going to emphasize for two simple slash optimizations. So with that said, first let's look at the statement of the problem. So we are given an integer n. So there is an undirected graph with n nodes, numbered from 0 to n-1. We are also given a 2D integer array called edges, where edges I equals ai bi, indicating that there exists an undirected edge connecting nodes ai and bi. So we are required to return the number of pairs of different nodes that are unreachable from each other. Actually, from the return statement, the nodes that are unreachable from each other, we can think of connected components, right? So that's a point of the problem. So let's look at the examples. So in example 1, the graph is singly connected, so all nodes can reach to each other, so the output is 0. In example 2, there are 3 connected components with nodes numbers 4, 1, 2. So the output will be 14. Basically, it's a count. For example, this 4 node cannot reach this 1 node, so we get 4 times 1. And this 4 node can also not reach this 2 node, so we get 4 times 2. And this 2 component also cannot reach each other, we get 1 times 2. So together we get 14. So that's the example, which also shed light on how to do the count. So before we look at the method, it's important to look at the constraint. So basically, the nodes can have a length up to 10 to the power 5th. In other words, so we cannot use purely brute force. So there are no repeated edges. So this is also an important assumption for this problem. So with that said, let's look at the method. The method we are going to use actually is a union find. We use union find to get connected components, and hence we get the number of nodes in each connected component. Then we do the count. So for this problem, actually I first tried union find using the vanilla union and do the count, but it does not pass. So here we did some optimizations and then it passes. So the two optimizations, though it's small, are the following. One is how to do the count. One is we use union by rank. So first, assume that we get m connected components after the union find operation, with numbers of nodes in each component xi, for example, x0, x1, x2, x3. Just take m equals 4, for example. So we use a, b, c, d just for the ease of writing. Then the result will be a times b, a times c, a times d. So this is the that node, the component a node cannot reach other nodes. This is the number. Similarly, we add b times c and b times d. So this is the pairs that we cannot reach from component b. So similarly for c times d. So notice that the order here is important. If we compute between x0 and x1, we can compute x0 times x1, and we cannot add x1 times x0 again. So this is the result. Then if we do a regrouping, so for example we compute those with b, we get a times b. So if we compute those with multiplication by c, we get a times c and b times c, so a plus b times c. And then we compute those with multiplication by d, we get a plus d, a times d, b times d, and c times d. This is a, b, c. So this a times b so actually it's the prefix sum, right? A when we times B, the A, and when we multiply by C, we get A plus B times C. And then if we multiply by D, we compute A plus B plus C times D. So this A plus B plus C times D is nothing but the prefix sum before D times D. So this is the prefix sum before C times C. So similarly here, this is the prefix sum before A times B. So in other words, it's a summation, the prefix sum between the current index, then times the value for current index. So this is nothing but the cumulative distribution function, if we like, or it's the count. So this is the one optimization when we do the count. The secondly is that when we use the union, the vanilla union, so we got a time limited exceeded result. So if we use union by rank, it's accelerated because we just it helps in doing the counting of their roots or parents. So we're going to implement a solution using union find, and when we do the union, we union by rank. So now with that said, let's look at the code. So now basically the procedure is standard. First the union rank, union find implementation. So for this, because this n is already given, I can actually directly initialize these things. I use a dictionary for I in range m. So initially, every node is its own root. So rack. So I'll first set all the racks to be 1 for I in range m. Then we do we implement the find and the union function. Let's first do the find function. So this is a routine. So it accepts 1 argument. So basically we will return I if I equals its roots. Otherwise, we're going to make a recursive call and call it on the roots of this I. So this is the find function, and then the union function. So originally I used the union, vanilla union. It does not pass, so I use union by rack, accelerate a little bit. So then we define union. So here it accepts 2 arguments, 2 nodes, you can think. And then first we find the roots of them. So it's find I, find J. Then what we want to do is that if the root I and the root J are the same, it means they are already in the same connected component. We do nothing. Otherwise, so we union them. If these 2 are not equal, what we want to do is that if we check the rack, if rack's root I is greater or equal than rack's of root J, so we are going to increment this by adding the racks of root J. The reason is that we set the roots of root J to be root I. So this is one part. So we set the root of root J to be root I, and then we increment the rack accordingly. Otherwise, we do the reverse. Let's copy this part, and then we set the root. We increment the root, the rack of root J by the rack of root I. Then we set root I has root, that is root J. So that's the union operation. So another thing we are going to use, let me write a function, the get components count. So basically what we want to do is for each of the different connected components, we count the number of nodes in it. So let's call a collections function, just call counter for convenience. So what we want to do is we find I for I in range m. So this is the routine. for each of the node, we find its root, and if their roots are the same, so we're going to group them together. So once we've done that, let's look at step 2. So do the union. So we iterate over the edges. So for AB in edges, so we're going to union AB and whole. So that's the main work actually. So once this is done, so we do the count. So as we specified above, we are going to use prefix sum or partial sum. So for this, first I'm going to call the get components function. Then we get the values. So I will make it a list. So once we do that, so we can do CDF for the first one. Then we are going to iterate from the second one, iterate from B and C and D here. So for I in range 1 to length of ox, that is the number of components, what we are going to do is that, let me initialize a result variable. So we increment the result by computing the CDF times the current value. So this CDF is before I, right? After this, we are going to increment this CDF by the current number. So once we've done this loop, we're okay. So we're going to return the result. So that's basically the solution. Let's first check for the special cases to make sure it works. So it passes the first one. So first one is sort of trivial case. Let's look at the second one. So we have this number of edge. We have 7 nodes. So then if we do this, it passes the second example. So now we are in a position to check if we can pass all the generic cases. So let's do some submit. Oh yeah, it passes the generic case. Let's do another run to see. Alright, so overall the method is a union find method. So we use union find to find the number of components, hence the nodes in each of the connected components. Then we do 2 slight optimizations. First is that the way we count the pairs. Second is that when we do the union, we use union by rank rather than the vanilla union. So with that said, I guess that's about it. Thank you very much.